Good morning, good afternoon, good evening, class. This is Mr. Arosena, and today we're going to finish up a little bit more on some more differentiation rules. Today we'll talk about implicit differentiation. Because previously, the first four sections of this chapter, we've been talking about explicit differentiation. Explicit differentiation is basically whenever we're given a function that is like y equals f of x. So here we have a function y equals something. Okay. Implicit differentiation allows us to deal with equations that are not written like this. So as an example, functions are sometimes described with two or more variables. A good example of this that we've dealt with a lot, maybe not a lot, but we've dealt with this earlier, is like a circle. Circle is described by the function x squared plus y squared equals r squared. And to make it easy on us, we'll consider, say, the unit circle. The unit circle has the equation x squared plus y squared equals 1. Okay, so this function is not written as y equals f of x. This function is written as the function depends on two variables x and y. Now, when dealing with a function like this, or if we're asked to differentiate this function, we kind of have two options. Option 1 is to rewrite the function as a function strictly of y. So rewrite to y equals f of x. Okay, and for this function it's fairly easy to do because we just go, wow, we can just use some algebra to write the following: 1 minus x squared, and then y equals square root of 1 minus x squared. And then we can differentiate this. So then y prime will then become, well, I'll rewrite this so it's 1 minus x squared to the 1/2. So when we differentiate this, just apply power rule into chain rule. So 1/2 1 minus x squared to the negative 1/2, and then chain rule this. The derivative of the inside here will just be negative 2x. Or in other words, this will simply be, this 2 will cancel that 2, so we get negative x over top of the square root of 1 minus x squared. It turns out that 1 minus x squared, well, that's just equal to y, so this is really just negative x over y. Okay, that's option 1, so rewrite to y equals f of x. But there's a second option. Option 2 is what is called implicit differentiation, and is what we'll work on here. Option 2 is differentiate implicitly. Jeez, I don't know how to spell this now. Differentiate implicitly. Okay, and implicit differentiation is not quite the same as explicit differentiation, which is what we were doing previously. So implicit differentiation, let me rewrite the equation that we were working with. X squared plus y squared equals 1. When we do an implicit differentiation, we write the following. We take the derivative of this with respect to x, take the derivative of this with respect to x, and take the derivative of this with respect to x. Okay? The first one's fairly easy because dx squared by dx is just straight power rule. Derivative of x squared is just x squared. The derivative of 1 is just a constant, that's 0. But this one's a little more interesting. So here we're asked to take the derivative of y squared with respect to x. Well, that's not, we can do that, but y squared is not really a function of x. So we can't really do that. Otherwise, we just end up getting like a 0 derivative. If y squared is not a function of x, it could be treated as a constant, so we can just ignore it. But we don't really want to do that. So what we're going to do instead is we're going to rewrite d by dx as follows. We're going to write this as d by dy of y squared. Purple. D by dy of y squared times dy dx as follows. And what this allows us to do then is now we can differentiate the y squared with respect to y. So we would get 2x plus, this becomes, derivative of y squared is 2y. And then we have a dy dx here. And dy dx, if you recall, is really just a derivative of my function. So dy dx is the derivative of the function. So now we just have to isolate for dy dx. So dy over dx is equal to negative 2x divided by 2y, or in other words, is going to be negative x over y. Okay, which is exactly the same as the derivative we got when we rewrote the function to be y equals. Okay? So those are two options when we deal with a function that is described in more than one variable. We can either rewrite the function so it's one of the variables is equal to some function of the other variable, or we just use implicit differentiation as shown here. Okay. Option 2 is always usable. Option 1, not so much, because let's say we have an example like this. Okay. Or here's an example. Can we apply the same idea to a function as follows? Okay. This function is actually really difficult to rewrite as a function as y equals some function of x. So I'm not even going to attempt it because I know it's difficult. It's a cubic function. We can't. There is a cubic function formula similar to quadratic function formula, but it's quite horrendous. And we would if we wanted to solve this for y, we'd probably use some kind of computer algebra system. So we're going to solve this implicitly. Okay, I'm going to solve this implicitly. All right. So let's go through this. So differentiate x cubed plus y cubed equals 6xy. Okay, and this particular function is sort of like a little background history. It's called the folium of Descartes, and it's a really neat function. If you feel curious to see what it looks like, graph it in Desmos. It looks really neat. All right, so to differentiate this implicitly, we'll take d by dx here. This will be d by dx, and then this will be d by dx. The first part's fairly easy, just derivative of x cubed, so that'll be 3x squared. We change this to a dy cubed dy times dy dx. Okay? Now if you're curious why we can do this, it's because when we write it like this, we can effectively cancel out the dy's, so it is technically the same as what it is up here. We're just putting the dy's in there to show us that we just take the derivative of y cubed with respect to y and have a dy dx at the end. Remember, that's the whole point of implicit differentiation. We want to get this dy dx, okay, so that we can eventually isolate for it and then get the derivative of our function. Now this part here, we'll have to retain a derivative of 6x times y, so we're going to have to use product rule because this is a product of functions. So product rule tells me that the derivative will be f times the derivative of y. The derivative of y is just dy dx. And then we add to it y times the derivative of x. X is just 6x, so the derivative will just be 6, like that. Okay. So we'll clean up a bit. We want to get the dy's by themselves. So we'll have 3x squared plus 3y squared dy dx equals 6x dy dx plus 6y. A bunch of algebra later, and we get the following. So I'm going to bring the 6x over and then factor out. So I'm going to bring this over to the left. So 6x dy dx going to the left. I'm going to factor out the dy dx. So I'm left with negative 6x plus 3y squared. I'm going to bring the 3x squared over to the other side. So we get negative 3x squared plus 6y. Divide everything by this negative 6x plus 3y squared, and we get the following. Our derivative is now equal to negative 3x squared plus 6y all over negative 6x plus 3y. And it looks like we can factor out a 3 from both of top and the bottom. So those can get changed. This becomes a 2, that becomes a 2. So we get 2y minus x squared over y minus 2x. There you go. And there's the derivative of that particular form of the folium of Descartes. Okay. All right. The key here is that when we take the derivative of a function of y, we can change it to this. Change it to dy cubed over dy times dy over dx. Okay, let's go through another example. Oh, we already did that one. So let's try another one. So here, differentiate a function sine x plus y equals y squared times cos x. Okay, so this one, we do the same thing. Let me just copy this out. So we'll do the same thing where we take, oops. Yeah, sorry. Okay, so we'll take this and we'll differentiate it. So we'll go d by dx of sine x plus y equals d by dx of y squared times cos x. Okay, let me just transfer it here. I'm going to definitely need a lot more room than my PowerPoint slide will give me. So we had written down d by dx of sine x plus y equals d by dx of y squared times cos x? Yeah, cos x. There you go. That looks like a lambda. There. Alright, let's differentiate. So we're going to differentiate d by dx of sine. So here we're going to have to apply the chain rule to this. So we'll get derivative of sine is cosine. Everything on the inside stays the same. Then we tag on the derivative of the inside function. So derivative of x is just 1. And derivative of y, well, that's just dy dx. There we go. Alright, and then this is all equal to the derivative of this. And this one we'll have to use product rule. So we'll go f times g prime. F times cosine has a derivative of negative sine x. When we add to it g times f prime, which is going to be d by dx of y squared. Or in other words, rather than writing it that way, I'm going to write it as dy squared dy times dy dx. And then this allows me to basically there we go. This allows me to rewrite this part. Well, derivative of y squared with respect to y is just 2y. Okay, time to clean things up a bit. Well, not really. Well, I have to expand and simplify. So let's expand this one. This one becomes cos x plus y plus cos x plus y. But this is now dy dx. Okay. This is all equal to negative y squared times sine x plus 2y cos x times dy dx. Okay. Some more algebra because we still need to isolate my dy dx's because we want to find out the derivative of my function, and the derivative is just dy dx. We're going to isolate the dy dx. So we're going to bring this to the left side and then factor out the dy dx. I'm going to bring this to the right side. So let's bring the dy dx to the left and factor it out. So we'll be left with negative 2y cos x plus cos x plus y. Notice I only factored out the dy dx, not the coses, or cosines, I guess. The cos x plus y is going to get moved to the other side. So we'll have negative y squared times sine x minus cosine of x plus y. Okay. After here, we'll just divide both sides by this monstrosity of an expression. So we get dy dx by itself. Oops, that's not an x. There we go. Dy dx is by itself. And now on the other side, we get what our derivative is equal to, which is negative y squared times sine x minus cosine times x plus y, all over negative 2y times cos x plus cosine times x plus y. Okay. We can't really do much to this other than some people would prefer not to have a negative y squared, so they would take out a negative 1 from the top and they would take out a negative 1 from the bottom. So you could rewrite this as y squared sine x plus cosine x plus y, all divided by 2y cos x minus cos x plus y. Some people would do that, some people might not. If you get to here, that's great. That is great. Because from here to here is just the multiplication of by negative 1. Or negative 1 over 1. Okay? Alright. Let's go through another one. One more example. I think I have one more example to go through. Okay, so here differentiate x e to the y equals to x minus y. Okay. So we'll start off as we did before. I think I can do this all on the PowerPoint slide. Oops. Okay, so we'll take the derivative of the first one, x e to the y, and we'll take the derivative of the second part. So this is dx by dx minus dy by dx. This is just 1. Derivative of x is just 1, so we can just leave it as 1. And we just erase this. There we go. So that's just 1. Okay, derivative of this will require the use of product rule. Okay, so product rule tells me that this will be x times derivative of this, which is just e to the y. Add to it the e to the y times the derivative. Oh wait, I almost forgot. This is going to be e to the y dy dx. Okay, because we're differentiating e to the y with respect to y times dy dx. Okay, then we'll add this to e to the y times the derivative of x, which is just 1. 1 minus dy dx. Okay, now we have to isolate the dy's, so we'll add this to the other side, move this to this side, so we'll get x e to the y dy dx plus dy dx equals not e to the y. Doing. It'll be 1 minus e to the y. There we go. Alright, dy dx gets factored out of this side. So we got dy dx. This is going to be x e to the y plus 1 equals 1 minus e to the y. And finally, our answer for the derivative of our function is 1 minus e to the y, all divided by x e to the y plus 1. There we go. Right. That'll be the last example. Now, a couple key things here. When you have a function in terms of y, like for example, like y cubed, if I want to differentiate y cubed, well, I go d by dx. But because there's no actual x in y, but we do know it's related to x, we can rewrite the d by dx as dy cubed over dy. So we can just take the derivative, or another way to think of this part is just take the derivative of y, of this function of y with respect to y, and then just tack on a dy dx at the end. So this really just becomes 3y squared dy dx. Okay? And you can actually apply this logic to basically any function, any function of y. So if I have, for example, I don't know, like cosine of y, we can just take the derivative of this as normal, keeping in mind we have a y instead of an x. So derivative of cosine is negative sine y, and then at the end of it, we'll just tag on a dy dx. Okay. That way, by doing that, you just kind of skip this middle step here. Okay. But remember, to go from here to here, what we're really doing is taking the derivative of the function with respect to y, and then just multiplying it by dy dx. Okay, these two are equivalent. These two are equivalent because my dy's just cancel out to go from one to the other. Okay. Alright, and that does it for my examples. If you have any questions, come see me in class. Here's the assignment for my class.